1 in 5,000 people carries a mutation that makes the aorta a slow ticking clock. The same gene shapes the whole body, tall, long-limbed, with an unusual reach and long, slender fingers. From outside, it can look graceful, full of apparent health. But the wall of the aorta is quietly coming apart, and the first sign is sometimes the last one. The gene is FBN1.
FBN1 sits on chromosome 15. It builds a protein called fibrillin-1, not an enzyme, not a receptor, but a scaffold. Fibrillin-1 chains link head to tail to form microfibrils, beaded cables, 10 nanometers across, threaded through the walls of the aorta, the skin, and the lungs. Everywhere the body needs to flex and spring back, fibrillin microfibrils are the frame those elastic fibers wrap around.
For most of medical history, Marfan syndrome was a clinical diagnosis, a checklist of unusual body proportions with no molecular anchor. In 1896, the French pediatrician Antoine Marfan described a 5-year-old girl with fingers so long they looked like spider legs, the case that would give the syndrome its name. Nearly a century passed before the gene was found. In 1990, researchers mapped the culprit to chromosome 15. Then, in 1991, Harry Dietz, Reed Pirates, Lynn Sakai, and their colleagues identified the mutation itself, a single letter altered in the fibrillin gene in patients with sporadic Marfan syndrome. Every change was new in the child. Neither parent carried it. Published in Nature, and a molecular era began.
The harmful variants in FBN1 span the whole gene. Missense changes, truncations, splice errors, deletions. Most disrupt the assembly of fibrillin-1 into microfibrils. The cables form, but they are fewer, or brittle, or fail to interlock at the right angles. About 1 in 4 cases carries a brand new mutation, no family history. In those who inherit it, the same fragile scaffold passes from parent to child.
Walk inside the aortic wall. Smooth muscle cells are stacked in layers, each sandwiched by sheets of elastic fiber. Those elastic sheets need a foundation, and that foundation is the fibrillin-1 microfibril lattice. The cables run through the medial layer like rebar through concrete, anchoring the cell layers and transmitting the pulse of every heartbeat into an orderly spring. When fibrillin-1 is defective, the lattice frays. The elastic lamellae lose their anchor. Under 50 years of pulsatile pressure, the wall expands, slowly at first, then faster, the aortic root widening millimeter by millimeter until it reaches the threshold for tearing. Now move to the eye. The ciliary zonule, the set of cables that suspends the lens, is made almost entirely of fibrillin-1. No elastin, pure fibrillin scaffold. When the fibrillin lattice fails, the zonule snaps. The lens slips upward, out of focus, out of position. Ectopia lentis, present in 6 of every 10 people with this condition. 2 organs, the same cable, the same failure.
But the scaffold is only half the story. Fibrillin microfibrils also function as a molecular leash. Tethered to the fibrillin cables through a linker protein is TGF-beta, a growth factor that drives tissue remodeling, inflammation, and cell dysfunction when it gets loose. In a healthy aortic wall, most TGF-beta is locked in an inactive complex, physically anchored to the fibrillin scaffold, unable to signal. When the scaffold fails, the leash breaks. TGF-beta floods the aortic wall. It drives smooth muscle cells toward a remodeling state, degrades the matrix, thins the wall. The result is not just structural weakness, but an active biochemical attack, a runaway growth factor loose in the aortic wall. But the same broken leash also explains the body you can see. Around the growing bones, the story runs in reverse. In healthy bone, fibrillin holds a reserve of TGF-beta in the sheath that wraps each growing bone. When fibrillin is missing, less is held there, and researchers think that missing break is what lets the long bones grow longer. Too much signal in the aorta, too little around the bone. One failed scaffold, 2 opposite faces. The tall, long-limbed build and the fragile vessel inside it.
And it is this runaway signaling that finally opened a door to treatment.
Marfan syndrome is a life lived near an invisible edge. Without monitoring or surgery, the median lifespan used to be around 32 years. Most deaths from aortic dissection, often without warning, often in young adulthood. Today, with serial imaging and the option of preventative surgery, the median has risen to around 72. 40 years of life recovered. But the aorta must be watched. Every year for life. When it reaches a critical width, surgeons replace the root before it tears. It is preventative surgery, deliberate and planned, not emergency repair. 2 lessons from the molecular biology pointed straight at treatment. First, slow the pounding. Beta blockers reduce the heart's contractile force and the pulse pressure that slams the aortic wall with each beat. A landmark trial in 1994 showed they genuinely slow aortic root growth. Second, cut the signal. If TGF-beta floods the wall when the fibrillin leash breaks, then blocking TGF-beta's downstream path should help. Losartan, an angiotensin receptor blocker first approved for blood pressure, does exactly that. It quiets the same signaling cascade that excess TGF-beta activates. A long-term study in adults found fewer aortic dissections and fewer deaths in patients using losartan. In a head-to-head trial in children, it worked about as well as a beta blocker, but no better. The answer for now is both approaches, often together, alongside lifelong imaging and surgery before the crisis. No cure, but a framework that gives most people with Marfan syndrome a nearly normal lifespan. 130 years. From a girl with spider legs and no name for her condition, to a molecular mechanism we can target, to the surgery that changes the outcome. The Marfan Foundation, built by families for families, has funded more than $23 million in research since 1986. They serve every person living with Marfan, Loeys-Dietz, or vascular EDS, any condition where the aorta holds the risk. Found in a lab, watched by a cardiologist every year, supported by a community. Find them at marfan.org. The Gene Channel.